Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 7th, 2025. We're looking at an ICLR conference paper, Copyright Protected Language Generation via Adaptive Model Fusion, published just over 3 months ago. This paper tackles how large language models, or LLMs, AI systems trained on vast text, can avoid reproducing copyrighted material. It introduces a new inference time method, Copyright Protecting Model Fusion, or CPFuse. This approach combines outputs from models trained on disjoint, or separate, sets of copyrighted material by adaptively blending their logits, essentially the raw scores for next words, to minimize copyright issues. Alright, so this figure on page 2 really helps visualize how Copyright Protecting Model Fusion works. On the left, imagine 2 separate training datasets, one with Harry Potter and another with The Hobbit. 2 large language models are trained, one on each. The key is at inference. That's when the model generates text. The Copyright Protecting Model Fusion algorithm then combines their outputs by minimizing the maximum Kullback-Leibler divergence. This Kullback-Leibler divergence is a mathematical way to measure how different one set of word probabilities is from another, ensuring the fused output, shown in green, stays balanced and avoids both original copyrighted areas. So how well does this balancing act actually work in practice? Well, this table on page 7 shows key copyright infringement metrics. It compares copyright protecting model fusion against other methods on datasets like Python code and creative writing. We see exact matching, or EM, measuring direct copies, where lower is better. For code, there's JP lag, a plagiarism score, again, lower is better. Copyright Protecting Model Fusion achieves very low scores here. Then there's the BLEU score. A lower value means less similarity to copyrighted text, and Levenshtein distance, where higher means more difference from it. Copyright Protecting Model Fusion consistently excels across these metrics. Building on those strong numerical results, this figure on page 8 offers a really clear visual. It shows histograms of exactly matched substring lengths. That's the length of directly copied text snippets for both Python code and math abstracts. We're comparing Copyright Protecting Model Fusion, shown in orange, against another method, CP delta, in blue. You can clearly see Copyright Protecting Model Fusion produces far fewer and much shorter copied segments. This visual comparison really drives home its ability to reduce that direct memorization, which is so important for copyright protection. Okay, so while reducing direct copying is great, we also need to make sure the model still produces useful and high-quality output. This table, also on page 8, looks at exactly that, utility metrics. For coding tasks, it shows pass at 1 scores. That's the percentage of times the generated code passes tests on the first attempt, so higher is better. For text, like writing prompts, it reports fluency, a measure of how natural and readable the output is. Copyright Protecting Model Fusion maintains very competitive scores, indicating it protects copyright without significantly harming the quality or usefulness of the generated content. Now, this figure from page 9 really drives home the point about maintaining utility. It shows specific examples of code generation errors. On the left, a method called memfree introduces a syntax error, a basic mistake in the code's grammar, by changing a variable name. On the right, memfree creates a logic error. The code runs but gives the wrong answer. In contrast, Copyright Protecting Model Fusion generates the correct code for that same problem. This clearly illustrates how some protection methods can harm output quality, a pitfall Copyright Protecting Model Fusion successfully avoids. Alright, so to understand how Copyright Protecting Model Fusion works internally, this figure from page 24 is very revealing. It shows 2 parameters, alpha and beta, evolving as text is generated using greedy decoding. That's where the model picks the most likely next word. These parameters dynamically weight the 2 base models. For these examples using overfitted models, models trained to memorize on the math abstracts dataset, notice how alpha and beta fluctuate. This constant adjustment ensures neither base model dominates, which is crucial for avoiding memorization. When these parameters plateau, the system just outputs padding tokens. That dynamic balancing we just saw is key, and it relies on an important assumption. This table on page 39 explores what happens when that assumption that the base models are trained on separate copyrighted data isn't perfectly met. It shows the overlap percentage, how much copyrighted material is shared between models. As this overlap increases, from 0 to over 66%, the EM, or exact matching score, which we want low, drastically increases. We also see ROU, or recall-oriented understudy, for gisting evaluation, a similarity score, go up, and quote LEU scores also rise, while LEV, the Levenstein distance, drops. All these changes mean more copying. This really highlights why having those separate datasets is crucial for the method's success. So that data separability is indeed foundational. To wrap up then, Copyright Protecting Model Fusion offers a really clever way to address copyright concerns. It works by combining multiple AI models, each trained on its own separate copyrighted material. The system adaptively blends their logits, those are the raw scores models give to potential next words, aiming to minimize KL divergence. That's a measure of difference in their predictions. The big takeaway is that this significantly cuts down on reproducing copyrighted content while crucially preserving output quality. It's a very promising and practical solution. Thanks for tuning in to the AI Research Roundup.